What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Take an ordinary ruler and cut the first meter into 10 equal pieces. Then cut one of those pieces again. Keep going. The marks become too close for your eyes, then too close for a microscope, then smaller than an atom, then smaller than the nucleus inside that atom. Nothing in the arithmetic tells you to stop. A line can always be divided one more time. Physics is not so generous. Far below the scale of atoms lies a length so small that it has become famous as the place where distance itself may stop behaving like distance. It is called the Planck length. Its value is about 1.6 times 10 to the minus 35 meters. That is roughly 20 powers of 10 smaller than a proton. If a proton were enlarged until it filled the observable universe, the Planck length inside that enlarged proton would be about the diameter of Earth. That comparison is already absurdly small, but the real shock is not the number. The real shock is what the number does not mean. The Planck length has never been seen. No experiment has discovered tiny cubes of space with Planck length edges. No detector has reached a final pixel and watched nature refuse to zoom farther. The Planck length is not a photographed brick at the bottom of reality. It is a warning produced by three ingredients that normally govern three different parts of physics. The speed of light sets the structure of space and time. The quantum of action, called the reduced Planck constant, sets the scale of quantum behavior. The gravitational constant sets the strength of gravity. Combine those three in the only way that produces a length, and the Planck length appears. So the famous smallest length is not an object found under a microscope. It is a number built from the rules we already know. The question is why those rules produce it at all. One answer sounds irresistible. Perhaps space is smooth only from far away. Perhaps at the Planck length, the apparent continuum breaks into indivisible units. That picture is easy to remember. It is also much more certain than the evidence allows. A second answer is stranger. The Planck length may not be the smallest piece of space. It may be the scale where the very act of asking for a smaller distance becomes physically confused. A ruler still has marks on paper. The equations still allow smaller numbers. But every known way of measuring a tiny region begins to disturb that region so violently that the measurement and the thing being measured can no longer be separated. That changes the governing question. We are not simply asking how small space can be. We are asking whether below the Planck length there is a smaller world waiting to be revealed, or whether the word below has lost the meaning we are trying to give it. The first useful answer is already here. The Planck length is not proof that space ends. It is the point where our ruler, our quantum probe, and gravity begin to disagree about what a measurement of distance would require. If the thought of a ruler failing before space does is worth carrying with you, subscribing is a small way to help me make the next documentary. And the ruler fails for a reason. Every measurement of length is really an event. Something leaves a source, crosses a region, interacts with an object, and returns information. A wooden ruler works because atoms in the ruler resist being pushed through one another. A microscope works because light scatters from an object and enters a lens. A particle collider works because particles strike one another, and the debris reveals structures too small to see directly. At human scales, those methods feel passive. The ruler seems to observe without changing the table. The light seems to illuminate without rebuilding the room. But there is no perfectly passive measurement. The smaller the target becomes, the more that fact matters. To locate something, the probing wave needs features at least as fine as the detail being sought. Long waves flow around small objects and carry little information about their shape. Short waves can resolve smaller structures. This is why visible light cannot show an atom as a little ball with a sharp surface. Its wavelength is far too large. Electron microscopes use the wave behavior of electrons with much shorter effective wavelengths. Particle accelerators push the same logic further by giving particles enormous momentum, which corresponds to a shorter quantum wavelength. The pattern seems simple. More energy buys a finer view. Then gravity enters the purchase. Energy gravitates. Concentrate more energy into a smaller region, and the gravitational effect of the probe itself grows. At ordinary laboratory energies, that effect is hopelessly tiny. At extreme energies, it cannot be ignored. If enough energy is packed inside a sufficiently small region, general relativity says the region can become hidden behind an event horizon. The instrument intended to expose the smaller distance may instead create a black hole that conceals it. This is the most famous physical route to a minimum measurable length. Push a quantum probe harder and its wavelength shrinks. Push hard enough and the energy needed to sharpen the probe curves spacetime strongly enough to defeat the measurement. One law says zoom in. Another says the zoom may close the view. The two trends cross near the Planck scale. That crossing is often presented as if it were a finished theorem. It is not. The argument mixes quantum reasoning with classical gravity, precisely where both are expected to need revision. It depends on how energy is localized, what counts as a measuring event, and whether a horizon really forms in the imagined setup. Different versions lead to different details. Some researchers argue that even the familiar claim that quantum gravity must become dominant exactly at the Planck scale is more heuristic than proven. But a heuristic can still be profound. It can reveal where our current concepts begin to push against one another. The black hole microscope does not prove a smallest length. It shows why smaller is no longer merely a matter of building a better lens. To understand how this boundary acquired its authority, it helps to return to a time before quantum mechanics, before general relativity, and before anyone knew what a black hole was. At the end of the 19th century, measurement units carried the history of human bodies and earthly objects. The meter had been linked to a fraction of the distance from the equator to the pole, then embodied in a metal bar. A second grew from the rotation of Earth. A kilogram lived in a manufactured object. These units were useful because they were shared, not because the universe had selected them. Max Planck wanted something deeper. In 1899, while studying the constants that appeared in the laws of heat and radiation, he noticed that certain fundamental constants could be combined to produce natural units of length, time, mass, and temperature. These units would not depend on a particular planet, nation, or artifact. Planck wrote that they would retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones. The constants available to him included the speed of light, the gravitational constant, and a constant that would soon bear his name. The last of these entered physics through the struggle to explain thermal radiation. It would become one of the central constants of quantum theory. Put the reduced Planck constant together with the gravitational constant and divide by the cube of the speed of light. Then take the square root. The result has the dimensions of length. That sentence sounds like mathematical cooking, so it is worth seeing what the ingredients carry. The speed of light is not merely the speed of one kind of particle. It sets the conversion between space and time in relativity and defines the fastest possible causal influence. The reduced Planck constant is not merely a tiny number attached to atomic physics. It converts between wave frequency and energy, and it fixes the scale of quantum uncertainty and quantum phase. The gravitational constant tells matter and energy how strongly they curve spacetime in general relativity. A length made from all three is therefore a place where causality, quantum action, and gravity meet in one unit. Nothing in that construction says space is made of little blocks. Dimensional analysis can reveal a natural scale without telling us what happens there. The speed of light can be combined with a year to make a light year, but that does not mean the universe is divided into light-year cells. A constant combination is a clue, not a microscopic photograph. For decades, Planck's natural units remained more elegant than urgent. Gravity was weak in laboratories. Quantum theory transformed atomic and particle physics without needing quantum gravity for ordinary calculations. General relativity transformed cosmology and astronomy while treating spacetime as a smooth geometry. The two frameworks could work almost independently because the domains in which each became dramatic were so far apart. Quantum theory dominates when action becomes comparable to the reduced Planck constant. General relativity becomes dramatic when mass and energy curve spacetime strongly. At the scale of an electron, gravity is negligible. At the scale of a star, the quantum wave nature of the star as a whole is usually negligible. Nature seems to have placed the two theories in separate rooms. The Planck scale is the door between them. Its related quantities make the door feel even stranger. The Planck time is the time light needs to travel one Planck length. It is about 5.4 times 10 to the minus 44 seconds. The Planck energy is immense by particle standards. The Planck mass is about 22 micrograms, roughly the mass of a tiny grain of dust visible to the eye. That mass sounds almost ordinary until it is compressed into a region comparable to the Planck length. This is one of the Planck scale's most useful surprises. The relevant mass is not fantastically large. The relevant density is. Quantum mechanics assigns a wave character to matter. For a massive object, one useful scale is its Compton wavelength. As the mass increases, that quantum wavelength shrinks. General relativity assigns a gravitational radius to mass. As the mass increases, that radius grows. For small masses, the quantum wavelength is far larger than the gravitational radius. For large masses, the gravitational radius can dominate. Near the Planck mass, The two scales approach one another, and both are near the Planck length. Picture two curves crossing. One is the quantum blur of an object. Add mass and the blur contracts. The other is the radius at which the same mass would become a black hole. Add mass and that radius expands. Near their crossing, the object cannot be described cleanly as either an ordinary quantum particle or an ordinary classical black hole. That crossing is why the Planck scale appears so persistently. It is not merely a clever unit system. It marks the region where the categories used by our best theories begin to overlap. But overlap is not the same as collapse. General relativity can be treated as an effective quantum field theory at low energies. In that form, gravity does not become meaningless merely because it is non-renormalizable in the old sense. Physicists can calculate definite low-energy quantum corrections without knowing the final high-energy theory. The situation resembles a map that works accurately across a country, even though it omits the atomic structure of the paper. The map has a domain of validity. Its incompleteness does not make every road fictional. This matters because the phrase, "our theories break down," is too blunt. At everyday and astronomical energies, quantum field theory and general relativity are spectacularly successful. Even quantum aspects of gravity can be discussed at low energy using effective methods. What fails is not every calculation. What becomes uncertain is the extrapolation toward regimes where the unknown short-distance structure can no longer be hidden inside small corrections. The Planck length, therefore, begins as a dimensional clue, gains force from competing quantum and gravitational scales, and becomes a frontier through thought experiments about measurement. None of those steps alone proves that it is the smallest possible length. The next step is to follow the measurement itself. What exactly must a probe do to reveal a smaller region? And what goes wrong before the answer arrives? Imagine trying to mark the position of a single particle inside a dark room. You send in one photon and wait for it to scatter back. If the photon has a long wavelength, its crest stretches across a broad region. The returning light can tell you that the particle was somewhere within that region, but not exactly where. To sharpen the position, you need a shorter wavelength. A shorter wavelength means greater momentum. The photon that gives you a more precise answer also delivers a harder kick. The act of locating the particle changes its motion. This is not a defect in the lamp. It is part of the structure of quantum mechanics. The uncertainty principle is often described as a limit caused by clumsy instruments. That description misses the point. Quantum objects do not carry simultaneously sharp position and momentum values, waiting for a careful observer to reveal them. A state that is tightly confined in position must contain a broad range of momenta. The sharper the location, the less sharply the momentum can be specified. This does not by itself create a minimum length. Ordinary quantum mechanics allows position uncertainty to be driven smaller, while momentum uncertainty grows without a final ceiling. The cost becomes enormous, but the equations do not place one last mark on the ruler. Relativistic quantum theory adds a complication. Once enough energy is concentrated in a small region, the probe can create new particles. The attempt to locate one electron more precisely than its Compton wavelength can supply enough energy for particle and antiparticle pairs to appear. The question, where is the original particle, becomes entangled with the fact that particle number is no longer fixed. Again, this is not necessarily a final length. It is a change in the language required. Single particle quantum mechanics gives way to quantum field theory, where particles are excitations of fields and can be created or destroyed. A failed description does not prove that nature has stopped. It may only mean the next description must carry more possibilities. Gravity makes the same lesson more severe, because the energy of the probe changes the geometry through which the probe travels. In the 1930s, the Soviet physicist Matvei Bronstein confronted the problem before quantum gravity had a settled name. He studied how quantum limits would affect measurements of the gravitational field. Electromagnetism could be quantized, while the laboratory remained a fixed stage. Gravity was different because its field determined the stage itself. To measure the field more precisely, one needed mass and energy. Yet concentrating mass and energy changed the gravitational field being measured. Bronstein recognized a limit that was not present in quantum electrodynamics. Density could not be increased without consequence. General relativity allowed the measuring apparatus itself to collapse. His work suggested that a quantum theory of gravity would require a deep revision of the concepts of space and time, not merely the addition of one more particle to an existing catalog. Bronstein was executed during Stalin's purges in 1938, at the age of 31. His scientific insight survived in a field that would spend decades rediscovering the same obstacle from different directions. In 1964, C. Alden Mead gave the measurement problem a sharper form. Consider locating a particle by scattering light from it. Shorter wavelength improves resolution. Higher energy strengthens gravity. If the measuring energy is confined too tightly, its gravitational field introduces an uncertainty that grows as the quantum uncertainty shrinks. Mead argued that the combined limit points toward a fundamental length of gravitational origin. The mechanism is easier to picture with an impossible camera. Its lens can use photons of any energy. Each time you demand a smaller feature, the camera selects a photon with a shorter wavelength. At first, the target is disturbed but visible. Then the photon becomes energetic enough to create a spray of particles. The camera adapts and records the whole quantum field. You demand another increase in resolution. The energy in the focal region rises again. Eventually, the focal spot becomes so compact that gravity can no longer be treated as a weak background effect. The camera is trying to illuminate a point with enough concentrated energy to place that point behind a horizon. The final image is not a smaller dot, it is missing information. This black hole picture carries enormous intuitive force, but each step contains assumptions. A real collision is dynamic, not a static ball of energy. Gravitational collapse depends on the distribution, direction, and duration of the energy. Quantum states do not occupy classical boxes with perfectly defined edges. A full theory of quantum gravity might prevent horizon formation, modify the uncertainty relation, spread the energy non-locally, or replace the entire setup with variables that do not resemble position. The lesson must therefore be stated at the right strength. Known physics gives serious reasons to expect that unlimited spatial resolution is not physically available in the simple way it is available in arithmetic. it does not yet tell us exactly what replaces that resolution, or whether all conceivable measurements face one universal minimum. This difference between a minimum length and a minimum measurable length is easy to lose. A minimum length would be a property of reality itself. It might mean no physical interval smaller than that value exists. A minimum measurable length would be a property of operations. Smaller intervals might exist in a theory, but no experiment could distinguish them. A third possibility is more radical. Below some scale, distance may not be fundamental at all. Asking for the separation between 2 points could be like asking for the temperature of one isolated molecule. The familiar quantity emerges only when enough underlying structure is present. Those possibilities can produce similar slogans and very different universes. Suppose a wooden table is made of atoms. There is a shortest meaningful scale for describing the grain of the wood as a continuous material. But there is no shortest distance in the room. The continuum description fails because the table has constituents. Now suppose a digital image is made of pixels. There is a smallest addressable picture element in that image. Zooming farther reveals blocks, because the image itself is discrete. Finally, suppose a road map records only connections between cities. The distance along the map may emerge from the pattern of links, even though no tiny piece of printed road serves as the ultimate unit. Quantum gravity proposals contain versions of all three ideas. Some make geometry discrete. Some retain continuity, but change what can be measured. Some treat spacetime as emergent from relations, information, or causal order. The Planck length is where these models often become different enough to matter. Before comparing them, one more trap must be removed. Small does not automatically mean energetic in every physical situation. Particle physicists often connect short distances with high collision energies because high momentum transfer resolves fine structure. This relation has been extraordinarily successful. It revealed nuclei, protons, quarks, and the structure of the weak force. But the Planck scale lies so far beyond current accelerators that the usual road becomes almost comical. The most powerful human colliders reach energies measured in trillions of electron volts for individual particles. The Planck energy is roughly a quadrillion times larger. Building a conventional circular collider to reach it would not merely require a larger tunnel. Synchrotron radiation, magnet strength, energy supply, and the size of the machine would all become overwhelming. Even a cosmic ray with extreme energy remains far below the Planck energy in the center of mass when it strikes an ordinary particle. Yet nature can amplify tiny effects through distance, repetition, coherence, and time. A Planck-suppressed change in the speed of light might accumulate over billions of light years. A minute rotation of polarization might build across the universe. A correlated fluctuation in spacetime might be searched for by comparing exquisitely quiet interferometers. A quantum phase can reveal a gravitational influence far weaker than any collision could expose directly. The frontier is not reached only by brute force. Sometimes, the better strategy is to let the universe perform the long experiment for us. This matters because the phrase "nothing" can probe the Planck scale is also too strong. Directly resolving a Planck length with a conventional microscope appears fantastically beyond reach. Constraining theories that predict Planck scale effects is already possible. The distinction is the same one used throughout physics. We do not need to touch the center of the sun to test models of nuclear fusion. We look for consequences that travel outward. The Planck length may cast shadows far larger than itself, but before searching for those shadows, we need to know what kind of thing could cast them. Does a quantum theory of gravity actually demand a smallest distance, or have generations of physicists allowed one compelling thought experiment to harden into folklore? The honest answer begins with an apparent embarrassment. Gravity can already be treated quantum mechanically in the regime where its effects are weak. That sounds like the central problem has been solved. It has not. It means the conflict is more precise than the usual claim that quantum mechanics and relativity cannot coexist. They can coexist as an effective theory. What we do not possess is a confirmed description that remains predictive without an ever-growing supply of unknown information as energy approaches the deep ultraviolet, the domain of shorter and shorter distance. An effective theory is not a defective theory. It is a theory that openly states the scale at which finer structure may matter. Fluid mechanics describes water without tracking every molecule. It predicts waves, pressure, and turbulence across a vast range. At sufficiently small scales, molecular physics takes over. The fluid equations were not false. They were organized around the degrees of freedom relevant to larger scales. General relativity can be handled in much the same spirit. At low energy, quantum corrections can be calculated. The long-distance effects are controlled by the particles and symmetries already known. Unknown high-energy details enter through additional terms whose influence is suppressed at low energy. This allows real predictions without pretending to know the ultimate theory. The trouble appears when the suppression stops being strong. More and more terms can matter. The theory requires more information from whatever deeper physics completes it. Near a characteristic high-energy scale often associated with the Planck scale, the useful hierarchy may fail. That is a limit of predictive organization, not a photograph of space breaking into cubes. A recent critical analysis has pressed this point further. The familiar arguments from dimensional analysis, quantum black holes, generalized uncertainty, and non-renormalizability may suggest the Planck scale, but suggestion is not prediction. Some assumptions used to make the scale inevitable are not established by the theories themselves. Quantum gravity could become important at the Planck scale, above it, below it, or through phenomena that do not map neatly onto a single energy. This criticism does not make the Planck length irrelevant. It makes the question better. Instead of repeating that physics certainly ends there, we can ask which parts of the claim are secure. The secure core is narrow and powerful. The Planck length is a natural scale made from quantum theory, relativity, and gravity. Multiple independent thought experiments point toward trouble with operational localization near that scale. Black hole thermodynamics expresses entropy using areas measured in Planck units. Several candidate theories produce new geometric behavior in the same neighborhood. No experiment has confirmed that the Planck length is an indivisible spatial unit. Everything beyond that core is a competition between models, and the models do not merely offer different answers. They disagree about what the question is made of. The first model to examine is the one we already use, because it reveals how easily the word failure can mislead. Imagine listening to a symphony through a wall. At low volume, the wall passes the broad rhythm and muffles the fine texture. You can describe what reaches you using a few features. As the volume rises, details that were negligible begin to matter. The wall vibrates, objects in the room resonate, and the simple description needs extra terms. Eventually, the original model of a passive wall is no longer enough. Effective field theory organizes physics by this same logic. It separates effects according to how strongly they matter at the energy being studied. The familiar equations sit at the front. Additional interactions are allowed, but each is accompanied by powers of a high energy scale that suppress its influence. At low energies, only a small number of terms matter. Predictions remain sharp. Gravity fits this structure. Quantize small ripples of the gravitational field around a smooth background, and the calculations produce gravitons, the hypothetical quantum excitations of that field. At ordinary energies, loops involving those quanta generate corrections that are fantastically small, but conceptually well-defined. The theory can predict the leading long-distance quantum changes to gravitational interactions without knowing the final microscopic structure of spacetime. This is one of the least appreciated facts in the entire subject. There is a low-energy quantum theory of gravity. Its effects are simply too weak for most direct measurements. Why, then, do physicists still speak of a quantum gravity problem? Because the effective theory does not remain economical at arbitrarily high energy. In a theory such as quantum electrodynamics, a finite set of measured quantities can absorb the infinities that appear in perturbative calculations. The theory remains predictive across its domain. For gravity, treated in the same straightforward way, higher orders require new terms with new coefficients. At low energy, those terms are suppressed and harmless. At high energy, the tower matters. The problem is not that the equations suddenly print nonsense. The problem is that prediction begins asking for more information than the low-energy theory contains. A coastline offers a useful carrier. From an airplane, a few numbers can describe its broad shape. Walk closer, and bays, rocks, and grains of sand appear. The measured length grows as the ruler shrinks, because more structure enters the account. No single large-scale map contains all possible fine detail. Effective field theory is the disciplined decision to use the map appropriate to the ruler in hand. At the Planck scale, the gravitational map may need the microscopic terrain. That terrain could still be continuous. A deeper quantum field theory might reach a high-energy fixed point, meaning its couplings settle into a controlled pattern rather than exploding. This is the idea behind asymptotic safety. In that picture, gravity may remain a quantum field theory all the way upward, not because nothing changes, but because the changes approach a stable ultraviolet regime. Asymptotic safety does not require spacetime to be a lattice of smallest cells. It changes the behavior of interactions with scale. Calculations using functional renormalization methods have found evidence for the needed fixed point in many approximations. but the full theory has not been established, and connecting the result to unique experimental predictions remains difficult. This is already enough to break the simplest binary. The alternatives are not merely smooth classical spacetime or pixelated quantum spacetime. A continuous quantum description with scale-dependent behavior remains a serious possibility. String theory begins from a different wound. In ordinary quantum field theory, elementary particles are treated as points. Interactions occur at exact locations. When gravity is included, the behavior of those point interactions at extremely short distance produces severe ultraviolet divergences. String theory replaces the point with a one-dimensional object. A string can vibrate in different patterns, and those patterns appear at low energy as different particles. The interaction is no longer concentrated at one mathematical point. Strings join and split across a small but finite world sheet. The violent short-distance encounter is spread out. One vibration mode has the properties expected of a graviton. Gravity is not added by hand after the theory is built. It appears among the allowed excitations. This is one reason string theory became such a powerful framework for quantum gravity. The string also changes what it means to probe a small distance. A point particle can be given more momentum, and, in the usual quantum picture, a shorter wavelength. A string responds differently. Add enough energy, and the string can excite higher vibration modes, or stretch. The probe becomes larger in the very attempt to make it resolve something smaller. High energy no longer guarantees unlimited spatial sharpness. A second clue comes from a symmetry called T-duality. Consider a spatial dimension curled into a circle. A string can move around that circle, but it can also wind around it. Momentum modes become more energetic when the circle is small. Winding modes become more energetic when the circle is large. Under T-duality, a theory on a circle of one radius can be equivalent to a theory on a circle whose radius is inversely related to the first. A very small circle and a very large circle can describe the same physics after momentum and winding exchange roles. That is not how point particles behave. It suggests that below a characteristic string scale, making the geometric radius smaller does not produce a genuinely new, smaller world. The description turns back into an equivalent larger one. The popular phrase is that string theory contains a minimum length. The precise statement is more careful. Certain operational attempts to distinguish distances below the string scale encounter dual descriptions or string spreading. The characteristic string length need not equal the Planck length exactly. Their relation depends on the string coupling and on how extra dimensions are arranged. In some scenarios, the string scale can differ substantially from the conventional Planck scale. String theory therefore weakens another common shortcut. Even a theory famous for minimum length behavior does not necessarily place one universal brick of size 1 Planck length beneath every direction of space. The strings themselves are not directly observed. Neither are the extra dimensions, supersymmetric partners, or the enormous landscape of possible compactifications often used to obtain low-energy physics. String theory has produced deep mathematical results and successful accounts of black hole microstates in special settings. It has also struggled to provide a unique, confirmed description of our universe. The relevant lesson is not that string theory wins, It is that one coherent approach can make the phrase below the minimum ambiguous without turning spacetime into a simple grid. Follow a string toward shorter distance, and the probe may spread. Follow a compact dimension toward smaller radius, and duality may return an equivalent larger description. In both cases, the limit appears through relationships, not through collision with a little wall. This is a recurring pattern. The deeper physics may not say no smaller distance exists. It may say two supposedly different distances are the same physical state. That possibility is difficult to picture, because daily life teaches us that smaller and larger are opposite. But physics has already broken similar intuitions. In quantum mechanics, a particle can occupy a superposition of paths. In relativity, observers can disagree about elapsed time while agreeing on the space-time interval. A variable that feels absolute can turn out to be part of a larger structure. String dualities suggest that geometric size may be one such variable. Now place this beside the black hole microscope. The microscope says, greater energy may conceal the target behind a horizon. String scattering says greater energy can enlarge the probe or reveal a dual description. These are not identical mechanisms, but they pressure the same starting model. Unlimited energy does not guarantee unlimited resolution. The next approach makes a more direct claim about geometry itself. General relativity says gravity is geometry. Matter and energy do not pull through an invisible force laid over space. They shape space-time, and free objects follow the resulting geometry. If gravity is quantum, perhaps geometry must possess quantum states, just as electromagnetic fields do. Loop quantum gravity begins by rewriting general relativity in variables suited to quantization. Instead of treating the metric, the direct measure of distances and times, as the only basic object, the theory uses connections and fluxes. These encode how geometric orientation changes and how areas are crossed. When the resulting operators for area and volume are studied, their possible measurement outcomes form discrete spectra. The values do not slide continuously through every real number. They come in allowed quantum amounts associated with networks of labeled links and nodes, called spin networks. The visual temptation is immediate. Draw the network as a web. Call each link a thread of space, and each node a tiny chunk. Announce that space-time has pixels. That picture can help and mislead at the same time. A spin network is not necessarily embedded in a pre-existing room, like wire inside a box. The network is meant to describe quantum geometry itself. Its links encode contributions to area where surfaces are crossed. Its nodes encode contributions to volume. The web does not sit in space. In the theory, the web helps constitute space. This is a much stranger form of discreteness than a checkerboard. A checkerboard has squares with fixed positions relative to a background. Loop quantum gravity is background independent. The relations among quantum states are primary. Smooth geometry is expected to emerge when immense numbers of quanta combine, much as a smooth surface emerges from atoms that are not themselves tiny smooth surfaces. The spectra of area and volume are discrete within the theory, but that does not automatically establish one smallest non-zero length that behaves like a universal ruler mark. Length operators are subtle. Different geometric quantities can have different spectra. Superpositions can blur outcomes. The relation between formal eigenvalues and a real measurement at the Planck scale depends on the full dynamics and on how matter serves as a reference. So even the most famous discrete geometry approach does not justify drawing identical cubes and calling the case closed. What it does provide is a concrete answer to one version of the question. Below the scale, where smooth geometry applies, the fundamental description may be a quantum state of relational geometry. Areas and volumes can be quantized. The continuum can be an approximation built from many excitations. If that is right, asking what lies between two neighboring quanta may resemble asking what ocean lies between two adjacent notes in a melody. The relation exists, but the assumed background in which an extra thing must fit may not. String theory had made small and large dual. Loop quantum gravity makes geometry itself a quantum observable. Both remove the ordinary ruler, but they remove it differently. That disagreement leads to the next question. If geometry is not fundamental, what is? A flash occurs. Later, a detector clicks. Whatever spacetime is made of, one event could have influenced the other only if a signal had enough time to travel between them. This before and after relation survives even when ordinary spatial pictures become unreliable. Causal set theory asks whether that relation may be more fundamental than distance. Its proposed foundation is a collection of events connected by causal order. One event can precede another, or the two can be unrelated because neither could influence the other. The set is locally finite, which means only a finite number of fundamental events occupy any finite spacetime region. Continuity is not assumed at the bottom. It must emerge when the causal set becomes large enough to resemble a smooth spacetime. The picture is not a stack of tiny cubes. It is closer to a genealogy without people. Each element records an event. The ordering records which events can be ancestors of which later events. From that network of precedents, geometry may be reconstructed statistically. Why should order contain geometry? In relativity, causal structure already carries most of the spacetime metric. The light cones at each event tell us which directions are time-like, light-like, or space-like. Add information about volume and the geometry can, under suitable conditions, be recovered. A causal set supplies order through its links and volume through counting elements. Distance becomes an emergent summary of causal relations. This offers a clean answer to the question of what exists below the Planck length. There may be no smaller continuous interval. There may instead be individual events and their order, with one element per roughly Planck-sized four-dimensional volume on average. The word roughly matters. A causal set compatible with relativity cannot simply be a rigid grid that selects a preferred direction. Elements are often imagined as sprinkled randomly into a smooth spacetime in a way that preserves Lorentz symmetry statistically. The randomness prevents the hidden structure from behaving like graph paper nailed to the universe. Causal sets remain a research program, not an experimentally verified foundation. The central challenge is dynamics. Many possible causal sets do not resemble smooth spacetime at all. A successful theory must explain why a universe like ours emerges with the right large-scale geometry, matter behavior, and cosmology. It must also produce distinctive tests. Still, the approach teaches an important lesson. Discreteness does not require a visible pixel pattern or a universal preferred frame. A discrete foundation can preserve relativistic symmetry in a subtler way. Causal dynamical triangulations starts from another kind of discrete construction. It builds candidate spacetimes from simple geometric blocks, then sums over many ways those blocks can be assembled while preserving a causal distinction between space and time. Computers explore the enormous family of possible geometries. The blocks are not automatically claimed to be literal atoms of spacetime. They can serve as a regulator, a temporary scaffolding that makes the quantum gravitational path integral calculable. The crucial question is what happens when the scaffolding is refined and a continuum limit is sought. This is similar to simulating a fluid on a mesh. The squares used by the computer do not prove water is made of squares. If predictions settle as the mesh becomes finer, the grid has helped define a continuous theory. If a physical minimum remains, that must emerge from the dynamics, not from the programmer's choice of block size. The simulations have produced a striking result. Across certain phases and parameter choices, a four-dimensional universe emerges at large scales. But a quantity called spectral dimension changes as the scale shrinks. Spectral dimension is best understood through an imaginary random walker. Release the walker into a space and ask how likely it is to return to its starting point after a given number of steps. In one dimension, escape routes are limited. In higher dimensions, the walker has more directions in which to wander. The return probability reveals an effective dimension even when the geometry is irregular. In causal dynamical triangulation simulations, the spectral dimension can approach 4 at large scales and fall toward about 2 at short scales. That does not mean two familiar dimensions simply disappear like floors removed from a building. It means diffusion through the quantum geometry behaves as though fewer independent directions are available. The effective dimensionality of spacetime may depend on the scale at which it is probed. Several other quantum gravity approaches show forms of dimensional reduction as well. That repetition is intriguing, but it is not yet a universal prediction confirmed by nature. Definitions differ. Approximations differ. A spectral dimension is not the same as the number of large directions seen in daily life. Even so, the consequence is enormous. The deep ultraviolet may not contain smaller versions of the same four-dimensional space. It may contain geometry whose effective rules are qualitatively different. A hallway does not become a narrower hallway. It becomes something in which hallway is the wrong category. This possibility connects back to the effective theory. The ultraviolet behavior of gravity might become more manageable if spacetime effectively loses dimensions at very short scales. Fewer directions can soften the way quantum fluctuations accumulate. In asymptotic safety, scale-dependent couplings and effective dimensional reduction can appear together in some analyses. In causal dynamical triangulations, the behavior emerges from numerical ensembles of geometries. Different roads may be pointing toward a related landscape, though no one knows whether they meet in the final theory. The landscape becomes stranger when information enters. A room seems to contain more information when it has more volume. Double the length, width, and height, and the number of possible microscopic arrangements should grow with the volume. That intuition works for ordinary matter until gravity is allowed to become strong. Pack more and more energy into the room. Eventually, the region becomes a black hole. A black hole is not simply another storage container. It's entropy, the quantity that counts how many microscopic states can correspond to the same outward appearance, scales with the area of its horizon rather than the volume inside. The Planck length appears in the denominator of that area law. Divide the horizon area by the square of the Planck length, then multiply by a fixed fraction and the Boltzmann constant. The result is the Bekenstein-Hawking entropy. This equation is one of the strongest clues in quantum gravity because it joins thermodynamics, quantum field theory, and general relativity in a result supported by several independent lines of reasoning. Yet it also creates a dangerous visual shortcut. An area measured in Planck units looks like a tiled surface. It is tempting to say each Planck area is one information pixel on the horizon. That can be a useful counting image, but the equation does not prove the horizon is literally covered in square tiles. The microscopic degrees of freedom depend on the theory used to explain the entropy. String theory counts particular brane and string states in special black holes. Loop quantum gravity counts quantum geometric states associated with punctures of a horizon. Other approaches use entanglement across the boundary or degrees of freedom in a dual theory. Several routes can recover the same area dependence without agreeing on the underlying objects. The shared fact is not the artwork, it is the scaling. Gravity tells us that the maximum information associated with a region behaves as though the boundary matters more deeply than the volume. This inspired the holographic principle, the proposal that the physics inside a region may be fully represented by degrees of freedom associated with a lower dimensional boundary. The word holographic invites the image of a three-dimensional scene encoded on a flat plate. That is only a loose analogy. The strongest concrete realization comes from gauge gravity duality, where a gravitational theory in a higher dimensional spacetime can be equivalent to a quantum theory without gravity on its boundary. Equivalent means more than similar. A state, process, or quantity on one side can be translated into a corresponding object on the other. Geometry with gravity can emerge from a quantum system described in fewer dimensions. This is not established as a complete description of our own universe. The best understood examples use spacetimes with properties different from the observed accelerating cosmos. But the duality has given physicists an exact laboratory in which spacetime is not fundamental in the ordinary sense. One of its most remarkable translations links geometry to entanglement. Entanglement is the quantum relationship that makes the state of a whole system definite even when its parts cannot be assigned independent pure states. In holographic theories, the entanglement entropy of a boundary region can be related to the area of a particular surface extending through the gravitational interior. Change the entanglement pattern and the geometry changes. Reduce the connections enough, and the smooth interior can begin to separate. This suggests a radical answer to what lies below the Planck length. Perhaps neither smaller lengths nor geometric atoms are primary. Perhaps spacetime is a large-scale organization of quantum information. Distance could express how strongly different parts of an underlying quantum state are connected. Two regions are close because the pattern of entanglement binds them tightly. They are far because the connection is weaker or more indirect. The geometry is a map of relationships. That idea remains incomplete outside controlled models. And entanglement alone may not be enough to build every feature of spacetime. But it changes the emotional center of the question. The bottom of space may not be more space. The ruler may be asking a network of quantum relationships to behave like a road. Black holes make that mismatch unavoidable. They force information, area, temperature, and geometry into the same equation. They also expose the most severe collision between quantum theory and spacetime, because a black hole can evaporate. The fate of the information carried into that evaporation will take us closer to what a Planck scale theory must actually preserve. Drop a book into a black hole. The book crosses the horizon carrying ink patterns, molecular arrangements, and every quantum correlation that distinguishes its pages from a blank stack of paper. To an outside observer, the black hole settles. Apart from mass, rotation, and electric charge, the details disappear from view. Classical relativity allows that concealment. Quantum theory makes it dangerous. Stephen Hawking showed that quantum fields around a horizon cause a black hole to emit thermal radiation. The black hole loses energy and shrinks. The radiation in the simplest calculation depends on broad properties such as mass, not on the detailed state of the book. Continue the process long enough, and the black hole can evaporate away. Where did the information go? Quantum evolution normally preserves information. This does not mean every practical detail can be recovered. Smoke from a burned book is hopelessly difficult to reverse. It means the final quantum state retains correlations that, in principle, distinguish one initial state from another. A perfectly thermal cloud with no such correlations would erase that distinction. The conflict is called the black hole information problem. It is not merely a question about archives falling into cosmic traps. It asks whether quantum mechanics, locality, smooth horizons, and ordinary spacetime can all remain true together. The Planck scale enters at two different places. First, the classical interior contains a singularity, a boundary of the space-time description where curvature grows without bound and the theory no longer supplies a complete continuation. Most physicists expect quantum gravity to alter this region, but no observation tells us the replacement. Second, as evaporation reduces the black hole toward Planckian mass and size, the semiclassical calculation becomes unreliable. The geometry can no longer be treated as a gently changing classical background with quantum fields laid over it. The end state may be a burst, a remnant, a transition to another configuration, or something not captured by those images. It would be easy to hide the whole information problem in that final unknown stage. Perhaps the last Planck-sized object releases everything. The difficulty is capacity. A large black hole can swallow an enormous number of possible quantum states. Asking a tiny final remnant to distinguish all of them creates its own theoretical problems. Asking the final burst to release the correlations may demand extreme and unnatural behavior. Modern calculations in holographic settings increasingly support the idea that the full evaporation process can preserve information. The entropy of the radiation can follow a curve that first rises, then falls as correlations emerge, ending near zero when evaporation completes. This is called the Page curve. The result is powerful, but the mechanism is not a simple movie of information climbing out through the horizon. The calculations use quantum extremal surfaces, replica methods, and gravitational path integrals. They reveal that the division between the black hole interior and the radiation is subtler than a fixed classical map suggests. At late times, parts of what classical geometry labels the interior can belong to the quantum information encoded in the radiation. That sentence is difficult because it pressures the ordinary idea that information must sit at one location. Quantum error correction offers a better carrier. A logical piece of information can be spread across many physical components so that no single component contains it, yet the whole can recover it. In holographic models, information about a bulk region can be redundantly encoded in boundary degrees of freedom. The geometric location is part of the code, not necessarily a separate container. This does not prove our universe is a quantum computer or that space is made of bits. It shows that a precise theory can reproduce geometric behavior while treating information as more fundamental than location. The black hole therefore refuses the naive Planck pixel twice. Its entropy uses Planck area, but several microscopic theories can account for that area. Its evaporation reaches Planckian uncertainty, but the resolution may involve global quantum encoding rather than one last local cell. A complete theory must explain why large black holes have smooth horizons for falling observers, why their entropy scales with area, how evaporation preserves or modifies quantum information, and what replaces the singular interior. It must also recover ordinary spacetime far from the horizon. No current approach has won every test. String theory offers strong evidence for unitary black hole evolution in settings where holographic duality is understood. It can count microstates for certain black holes and reproduce the entropy. The price is a framework with many possible low-energy realizations and no unique experimentally confirmed path to our cosmos. Loop-based approaches can replace the classical singularity in symmetry-reduced models and assign quantum states to horizons. The price is the challenge of deriving full dynamics, connecting cleanly to observed low-energy particle physics, and extracting distinctive predictions. Causal set and triangulation approaches make the causal or combinatorial structure primary. They must show that black hole formation and evaporation emerge with the correct semiclassical behavior. Asymptotic safety seeks a controlled high-energy completion within quantum field theory. It must establish the required fixed point beyond approximations and turn it into measurements that distinguish it from competitors. The disagreement is not evidence of failure in the ordinary sense. It is evidence that the same known clues underdetermine the microscopic answer. Area law, Hawking radiation, low-energy gravity, and quantum information constrain the destination without supplying one road. That is why experiments matter, even when they cannot touch a Planck length directly. A theory that modifies spacetime at short distance may alter how waves propagate over long distances. It may break or deform Lorentz symmetry, the principle that the laws of physics take the same form for observers moving steadily relative to one another. It may rotate polarization, change particle thresholds, add noise to interferometers, or modify the dispersion of gravitational waves. But no effect is universal. Discrete geometry does not automatically mean light travels at different speeds. A model can preserve Lorentz symmetry exactly. A theory can contain a minimum operational length without producing a preferred rest frame. The absence of one signal can kill one mechanism while leaving the broader idea untouched. This is the most important rule for reading Planck scale experiments. They do not test the phrase quantum gravity as a single object. They test particular predictions made by particular models. The sky has supplied some of the longest baselines available. A gamma-ray burst can release photons across a broad range of energies from a source billions of light-years away. If a quantum gravity model makes the vacuum slightly dispersive, high-energy photons and low-energy photons may travel at minutely different speeds. Across a laboratory, the difference would be invisible. Across the universe, it might accumulate into a measurable delay. The challenge is that the source itself may emit different energies at different times. An observed delay can be astrophysical rather than fundamental. Researchers therefore compare multiple bursts, use conservative assumptions about emission, and test how strongly any propagation effect can be bounded. One short gamma-ray burst observed by the Fermi spacecraft became especially important. It produced a very high-energy photon soon after the burst began. The arrival time placed strong limits on models, with a leading change in photon speed, proportional to energy over the Planck scale. Later analyses using several bright bursts strengthened robust constraints. The result is often summarized as light travels normally even at the Planck scale. That is too broad. The observations constrain certain energy-dependent violations of Lorentz invariance. They do not show that spacetime is smooth at every scale, and they do not rule out quantum gravity theories that preserve the symmetry or predict different effects. Polarization offers another long lever. Light can be decomposed into different polarization states. Some models predict vacuum birefringence, meaning those states propagate differently through empty space. Over cosmological distances, even a tiny difference can rotate or scramble the observed polarization. Detecting strong linear polarization from a distant gamma-ray burst implies that such rotation was not large enough to erase the pattern. Measurements with the Integral Observatory improved constraints on certain birefringent Lorentz violating effects by several orders of magnitude. Again, a corner of theory space narrowed. Spacetime did not confess its microscopic structure. This distinction protects both truth and wonder. A null result is not nothing. It is reality, refusing to behave in one proposed way across billions of years of travel. The universe has already performed an experiment no laboratory could afford. Photons cross the cosmos while carrying phase, energy, and polarization. They arrived without the distortions several models expected. The Planck length remained unseen, but some of its possible shadows did not appear. Gravitational waves provide a newer messenger. If gravity propagates differently at different frequencies, waves from merging black holes and neutron stars can arrive with altered phases. The waveform acts like a long sentence whose syllables would drift out of order if dispersion were present. The International Gravitational Wave Detector Network compares observed signals with the predictions of general relativity. Tests have found no evidence for the modified dispersion patterns examined so far, and have tightened bounds on alternatives, including a non-zero graviton mass and some Lorentz violating terms. Once again, this confirms general relativity within the tested regime. It does not prove that no quantum geometry exists. The wavelengths involved are enormous compared with the Planck length. The experiments are sensitive only to models that translate microscopic structure into an accumulated macroscopic change. So the sky has done something precise. It has not shown us what space-time is made of. It has shown us several things it is not allowed to do, at least not strongly enough to have escaped detection. The next search brings the question indoors, into rooms where mirrors, photons, suspended masses, and quantum states can be controlled one noise source at a time. An interferometer turns distance into a disagreement between waves. Split a laser beam along two paths. Reflect both parts from mirrors. Bring them back together. If the paths are identical, the returning waves combine in a predictable pattern. If one path changes by a tiny amount, the crests and troughs return with a different alignment. Bright regions dim, dark regions brighten. A change far smaller than the width of an atom becomes visible through phase. This is how gravitational wave observatories measure distortions smaller than a proton across arms kilometers long. It also inspires attempts to search for a more restless space-time. The simplest pixel picture suggests that distance should jitter as measurements approach some fundamental grain. But a Planck length of random motion at each instant would usually average away, and many naive versions are already incompatible with observation. More sophisticated models predict correlations spread across the apparatus. The signal is not one mirror hopping by one Planck length. It is a distinctive relationship between measurements made in different directions or at different times. The Fermilab holometer was built to search for one family of such correlated effects. Two neighboring interferometers, each with arms about 40 meters long, operated at very high frequencies. Ordinary disturbances affecting one instrument, but not the other, could be rejected. A genuine shared space-time fluctuation might appear in the cross-correlation. The holometer did not discover a universal grain of space. It constrained specific models of holographic or exotic correlated position noise. Some early proposals were ruled out or pushed into narrower forms. The broader question survived because the predicted signal depends strongly on geometry, frequency, and the model used to connect quantum information with measurable position. This is science behaving exactly as it should. A bold idea is translated into a waveform. Mirrors listen. The absent waveform removes that version of the idea. New experiments are trying different geometries and different readouts. The gravity from the quantum entanglement of space-time experiment, known as G-Quest, uses tabletop interferometers and a photon counting technique. Conventional interferometers often infer tiny phase changes from variations in a large stream of light. Photon counting can instead focus on individual photons appearing in an output that should be nearly dark. Under the proposed operating conditions, this can improve sensitivity to particular high-frequency spacetime fluctuation models. The target is not the Planck length itself as a visible step. The target is a predicted statistical pattern, a faint excess of correlated photons with a specific spectrum and geometry. If the pattern appears, the difficult work begins. Instrumental noise, unknown backgrounds, and alternative physics must be excluded. If it does not appear, the geometric models used to predict it will lose room. That is a far more disciplined proposition than asking an interferometer whether space is pixelated. Another experiment stretches a quantum path through 50 kilometers of optical fiber while remaining on a laboratory table through coils. A single photon can travel in a superposition of two routes placed at slightly different gravitational potentials. General relativity predicts a tiny difference in phase because clocks, and therefore waves, evolve differently with gravitational height. Researchers have demonstrated phase sensitivity sufficient to resolve the expected modulated gravitational signal in such a system. This is a major technical step at the meeting point of quantum interference and gravity. It is not a detection of quantum gravity. The gravitational field in the experiment can still be described classically, while the photon is quantum. The result tests quantum matter and light operating in curved spacetime. That territory is valuable because any future quantum gravity test must first master ordinary gravitational phases, noise, stability, and quantum coherence at extraordinary precision. The road to the deepest theory may begin by proving that a single photon can carry a gravitational phase through enough fiber without the laboratory drowning it. A second experimental strategy asks whether gravity can create entanglement between masses. Place two tiny objects near each other. Prepare each in a quantum superposition of positions. Shield electromagnetic interactions as completely as possible. If the gravitational interaction depends on the branch positions, the joint quantum state can acquire correlations. Under certain assumptions, observing entanglement would imply that the mediator of the interaction possesses quantum features. A purely classical communication channel could not generate entanglement from initially separate states. This proposal transformed quantum gravity from a distant energy problem into a control problem. The masses need not reach the Planck energy. They need to remain coherent while gravity has enough time to imprint a phase. The experiment trades brute force for isolation. The practical obstacles are severe. Gravity between microscopic masses is weak. Casimir forces, stray charges, magnetic contamination, vibration, thermal radiation, gas collisions, and ordinary decoherence can overwhelm it. The superposition must be created, maintained, and verified. Every non-gravitational path to entanglement must be excluded. The interpretation has also become more contested. Recent work has shown that some local theories described as classical gravity can generate quantum communication and entanglement when matter is treated within quantum field theory rather than a simpler particle model. That challenges the claim that any observed gravity-mediated entanglement would, by itself, be an unambiguous proof that the gravitational field is quantized in the expected way. Other analyses argue that carefully designed experiments can still discriminate classes of models through scaling, locality, or additional observables. The frontier has not vanished. The decisive question has become sharper. Would entanglement show that gravity is quantum, or only that the full interaction between quantum matter and a gravitational structure cannot be represented as a classical information channel of the simplest kind? That may sound like retreat. It is progress. The experiment now has to separate more precise alternatives. There are even proposals to detect a single graviton indirectly through the transition it induces in a massive quantum sensor. Gravitons, if they exist as ordinary quanta of the weak gravitational field, interact so feebly that direct detection has long been treated as practically impossible. New ideas exploit resonant quantum systems, enormous coherence, and carefully chosen astrophysical sources. No single graviton has been detected. Whether a convincing experiment can be built remains uncertain, but the proposal reveals how the field has changed. Quantum gravity is no longer discussed only through unreachable colliders and the beginning of the universe. Researchers are designing devices whose possible outcomes can distinguish pieces of the problem. The experiments do not all ask the same question. Interferometers search for model-specific spacetime fluctuations. Quantum path experiments test the compatibility of coherence with gravitational phase. Entanglement proposals test whether gravity can mediate quantum information under controlled conditions. Graviton sensors seek the particle character of weak gravitational waves. Astronomical observations test whether high-energy messengers accumulate dispersive or birefringent effects. Together, they form a ladder of evidence. The first rung asks whether quantum systems respond to classical gravity as expected. They do, within increasingly sensitive tests. The next asks whether gravity can preserve, transmit, or generate genuinely quantum correlations. Experiments are approaching that territory, but interpretation remains debated. A higher rung asks whether the gravitational field itself has observable quantum fluctuations or individual quanta. That remains open. The final rung asks which microscopic theory produces spacetime, black holes, and the early universe. No current experiment has reached it. This latter prevents a common mistake. Proving that gravity has quantum features would not immediately prove string theory, loop quantum gravity, causal sets, or any other full framework. It would establish a property that successful theories must reproduce. Likewise, failing to see one predicted noise spectrum would not prove spacetime is continuous. It would remove one bridge between microscopic theory and the instrument. The Planck length sits at the top of this ladder as a natural scale, but the experiments climb from below. They use macroscopic coherence, long baselines, low noise, and repeated measurements to test consequences that can be magnified. There is a quiet reversal here. The smallest meaningful scale in known physics may be approached using some of the largest and most delicate quantum objects humans can control. A grain of dust placed in two locations. A photon stretched across 50 kilometers of fiber. Mirrors separated by rooms, tunnels, or continents. A flash that has crossed the universe. The ruler has become an entire experimental world. Yet one arena remains beyond any laboratory's ability to reproduce. The universe itself once occupied conditions in which energy, curvature, and quantum behavior were far more extreme than they are now. The phrase Planck time is often used as though it names the first tick after creation. That phrase hides the same uncertainty as the Planck length. To understand what it really means, we must run the cosmic expansion backward until the equations reach the edge of their authority. The expanding universe is not an explosion moving outward into an empty room. It is a change in the geometry that defines distances between large-scale co-moving locations. Run that expansion backward, and matter becomes hotter, denser, and more energetic. The cosmic microwave background reveals a time when the universe had cooled enough for light to travel freely. Nuclear abundances reveal an earlier furnace in which the light elements formed. Particle physics lets the reconstruction continue towards still higher temperatures. Eventually, the extrapolation reaches energies where the unknown quantum behavior of gravity may matter. The corresponding time is called the Planck time, about 5.4 times 10 to the minus 44 seconds. It is often described as the earliest possible moment. That claim is not established. The Planck time is the time light takes to cross one Planck length. Like the length itself, it is constructed from the gravitational constant, the speed of light, and the reduced Planck constant. It marks a natural scale at which familiar extrapolations may require new physics. It does not prove that time advanced in indivisible Planck ticks, that there was a first tick, or that the universe began exactly one Planck time before our theories became usable. The classical equations of general relativity lead toward a singular boundary when applied to a sufficiently simple early universe. A singularity theorem tells us that under broad conditions, past directed paths cannot be extended indefinitely within the classical spacetime. It does not supply a physical photograph of an infinitely dense point. It tells us the classical description is incomplete. Quantum gravity proposals replace that incompleteness in different ways. Some loop-inspired cosmological models replace the classical singularity with a bounce. A contracting phase reaches a maximum density and transitions into expansion. Some string-based scenarios begin with extended objects, dual phases, or earlier cosmological branches. Other models treat the beginning as a transition in an emergent spacetime, where the ordinary time coordinate appears only after a more fundamental quantum state organizes itself. Inflationary models can push observable structures back to quantum fluctuations during an accelerated expansion, but inflation itself requires an initial state and a high-energy description. None of these possibilities has been confirmed as the history of our universe. The early cosmos can still carry clues. Quantum fluctuations stretched by expansion may have seeded the density variations that later grew into galaxies. The statistical pattern in the cosmic microwave background strongly supports an early phase in which tiny fluctuations became cosmic structure, though the precise mechanism and inflationary model remain unsettled. Primordial gravitational waves would offer another messenger. Their pattern could reveal the energy scale and dynamics of the early universe. Searches for the distinctive curling polarization pattern they would leave in the microwave background have produced increasingly strong limits, but no confirmed primordial signal. Even a detection would not automatically expose Planck-scale discreteness. Most inflationary models operate below the Planck energy. The signal would constrain the physics of the early universe, and perhaps narrow quantum gravity models, not display the final microscopic layer. A subtler issue is called the trans-Planckian problem. In some inflationary histories, modes observed today can be traced backward to wavelengths smaller than the Planck length. Standard calculations continue treating those modes as ordinary quantum fields on a smooth spacetime. If the microscopic theory changes at short distance, could it leave a trace in the final spectrum? Models have proposed oscillations, altered correlations, or non-standard initial states. But the predictions depend on assumptions about the unknown ultraviolet physics, and the effects can be suppressed or confused with more ordinary features. No accepted trans-Planckian signature has been found. The problem is a cosmological version of the impossible ruler. The equations invite us to run a wavelength backward through the Planck boundary, while the physical meaning of that continuation is exactly what remains uncertain. This brings the whole investigation back to the original act of division. Arithmetic allows 1 meter to be halved forever. Physics asks, what operation would make each new half real as a distinguishable measurement? At ordinary scales, a ruler and a light pulse are enough. At atomic scales, quantum waves and fields replace sharp trajectories. At still shorter scales, particle creation changes the meaning of locating one object. When gravity becomes inseparable from the probe, the geometry being measured joins the experiment. The Planck length appears because 3 rules meet there. Quantum theory makes fine resolution expensive in momentum and energy. Relativity ties energy to causality and spacetime. Gravity lets concentrated energy reshape the region under examination. The familiar conclusion says space stops. The evidence supports a more interesting conclusion. Our ordinary concept of distance may stop being fundamental. That is not the same as saying nothing exists below. Several possibilities remain alive. There may be a continuous quantum spacetime whose interactions approach a controlled high-energy regime. There may be strings whose spreading and dualities make shorter distances physically equivalent to larger descriptions. There may be discrete spectra of area and volume carried by relational quantum geometry. There may be a locally finite causal order from which smooth spacetime emerges. There may be a sum over fluctuating geometries whose effective dimension changes with scale. There may be a holographic description in which distance records the organization of quantum information. There may be a structure none of these programs has yet imagined. These are not equally developed in every respect, and they are not established facts. They are serious attempts to make the same set of clues coexist. Any successful answer must recover the smooth spacetime of general relativity at large scales. It must preserve the extraordinary accuracy of quantum field theory. It must account for black hole entropy and evaporation. It must explain why Lorentz symmetry survives the tests already performed, or predict exactly how it fails within the remaining bounds. It must produce a universe like the one observed, and it must expose at least one consequence that distinguishes it from its competitors. The Planck length alone cannot choose among them. That is the answer boundary. It is a natural and probably important scale. It is supported as a meeting point by dimensional analysis, quantum localization arguments, gravitational collapse heuristics, black hole thermodynamics, and many candidate theories. It is not an experimentally observed smallest distance. It is not a confirmed pixel size. It is not known to be the exact energy at which every approach to quantum gravity becomes unavoidable. The word probably deserves attention. A scale can be physically profound without being a hard wall. The mass of a proton marks the energy of strong interaction structure without being the only scale in nuclear physics. The atomic scale marks where chemical intuition changes without forbidding shorter distances. The Planck scale may be a transition region, a family of related scales, or a clue whose final role will look different once the deeper variables are known. There is another reason the final answer cannot be compressed into one measurement of one length. A length becomes observable only through a theory of the apparatus. A detector records clicks, voltages, phases, tracks, temperatures, and correlations. Distance is inferred from those records using a model of light, matter, clocks, and gravity. At the Planck frontier, the model of the apparatus is part of the dispute. A string-based probe may spread as energy rises. A loop-based geometry may allow only certain area outcomes. A causal set may produce fluctuations in counting and order. An emergent spacetime may alter correlations without introducing any local grain. Two theories can agree that direct resolution fails while predicting completely different detector records. This is why the decisive experiment will probably not display a final ruler mark. It will reveal a pattern that one framework expected and another could not reproduce without changing its foundations. The pattern might be a frequency dependence rather than a size. It might be a correlation between separated instruments. It might be a departure from ordinary quantum coherence that scales with mass and separation. It might be a black hole signal whose late time structure preserves information in one way and not another. It might be a cosmological correlation with a shape that survives every conventional explanation. Even the value called the Planck length may enter only as the scale suppressing the effect. The detector could be meters long and the signal could unfold over hours. The microscopic theory would be present through the ratio between the laboratory scale and the Planck scale, repeated across an enormous number of quantum events. A single raindrop cannot carve a canyon. A river can, because the small action is repeated and organized. Planck scale phenomenology searches for the equivalent organization. Distance, duration, coherence, or the number of particles can allow a tiny correction to accumulate. The analogy has a limit. Quantum effects can cancel as easily as they accumulate. Noise can grow faster than the signal. Some symmetries forbid the correction entirely. The useful question is never whether a tiny effect could somehow become large. It is which theory predicts a coherent pattern that survives averaging and cannot be imitated by the apparatus. This is also why negative results deserve careful language. They can exclude a predicted coefficient, symmetry violation, or noise spectrum. They cannot exclude every unknown structure that someone might place near the Planck scale. A theory that makes no accessible prediction remains possible in a logical sense, but it becomes difficult to separate from imagination. The future of the subject, therefore, depends on a double achievement. Theorists must turn deep ideas into risks. Experimentalists must build instruments quiet enough to let reality accept or reject those risks. What then really exists below the Planck length? The scientifically honest answer is that no observation has told us, but honest ignorance is not an empty ending, because the investigation has removed several false answers. We know that the Planck length is not simply the smallest mark printed on a cosmic ruler. We know that its importance comes from the collision of quantum resolution with gravitational back reaction. We know that a minimum measurable distance, a discrete geometry, and an emergent notion of distance are different claims. We know that black hole area measured in Planck units does not by itself prove literal tiles. We know that astronomical observations have already excluded some ways Planck-scale physics might distort light and gravitational waves. We know that laboratory experiments are beginning to test quantum coherence, entanglement, and model-specific space-time fluctuations in the presence of gravity. The frontier has moved from a slogan to a set of discriminating questions. Does increasing energy eventually enlarge the probe rather than sharpen it? Are geometric measurements quantized? Is causal order more fundamental than position? Does effective dimension change? Can space-time fluctuations produce a correlated photon pattern? Can gravity mediate quantum information in a way no classical model can reproduce? Does black hole evaporation reveal a quantum code in which location itself is emergent? Each question has a possible witness, a scattering event, a spectrum, a simulated diffusion process, a gamma ray crossing the cosmos, two interferometers comparing darkness, two masses trying to remain quantum while gravity acts between them, radiation carrying correlations from a black hole. This is why the Planck length matters, even before anyone measures it directly. It forces physics to turn the measuring device back on its own assumptions. The ruler assumed a background that stayed still. The photon revealed that measurement disturbs the target. Relativity revealed that energy changes time and distance. The black hole revealed that too much resolution can hide information. Quantum information revealed that what appears to be inside a region may be encoded through relationships that do not respect the classical map. The object under investigation changed at every step. First, it was a length. Then it was an operation. Then it was geometry. Finally, it became the question of what makes geometry possible. That is the beyond click gain. The smallest distance is not only a problem of size, it is a problem of ontology, but not in the vague philosophical sense. It is a precise demand for the variables that a future experiment can distinguish. Suppose tomorrow, an interferometer detects a correlation matching one quantum spacetime model. That result would not allow us to announce that every Planck cell had been found. It would establish one behavior. Other instruments would have to reproduce it. Competing explanations would have to fail. The signal would need to connect with black holes, cosmology, and low-energy gravity. Suppose instead, the next generation of experiments finds nothing. That would not restore a perfectly smooth classical spacetime at every scale. It would tell theorists that the microscopic structure hides more effectively, preserves more symmetry, appears at another scale, or leaves a different kind of trace. Either outcome changes the map. There is a temptation to treat inaccessible scales as places where imagination has no limits. The opposite is true. The farther the experiment lies from direct reach, the stricter the logic must become. Every proposed picture has to repay its beauty with a prediction, a consistency test, or a connection to known physics. The tiny cubes are beautiful. The vibrating strings are beautiful. The spin networks, causal orders, changing dimensions, and holographic codes are beautiful. Beauty keeps people looking. It does not decide what is there. Reality decides through consequences. For now, the Planck length is the sharpest place where the consequences of our existing theories point toward an unknown structure. It is a number that tells us not that space certainly ends, but that the ordinary ruler has reached the edge of its jurisdiction. Below that edge may lie smaller distances. It may lie a dual description in which smaller returns as larger. It may lie quantum geometry without a background. It may lie causal relations without continuous position. It may lie information from which distance emerges. Or the word below may be the last remnant of a picture nature no longer uses. The final truth is therefore more dramatic than the pixel claim and more restrained than certainty. Space has not been proven to stop at the Planck length. Our present way of asking space how small it is does.